So good afternoon, everybody. Can you hear me? Thank you. Okay, good afternoon. So today is the first sessions on the tutorial sessions that we would like to talk about the transformers. So here, as I point out, okay, to you that we have a combined exercise on the transformers, actually for each chapters. Here is the exercise I combined for the transformer chapters. First, we start for the single phase transformers. That there are several examples. Follow the examples. There are several problems that you can exercise with the problems. Following the problems, there are several examples of the past exam papers. So with some of the solutions for your reference. Okay, so now we can start with the first examples that is about the ideal transformers, which actually is talking about the turns ratios, transformation ratios, their difference, and their common points. We start with the ideal transformers. So can you see that the exercise here? So it depends on your devices you use, maybe the front, right? The size, the font, depends on your devices used. Example 1 showing the general relationship between the turn number ratios and the current ratios between the primary and the secondary. So which is a straightforward exercise. The question said, the example says that the high voltage side of a transformer has 500 turns, while the low voltage side has 100 turns. When connected as a step-down transformer, that means the primary side is higher and secondary side is lower for the voltage. The load current is 12 amperes. The loading current is 12 amperes. This means that the secondary loading current is 12 amperes. That's the meanings. So the question given that one, the primary side, because this is a step-down transformer, the primary side is a high voltage side. The secondary side is low voltage side. Primary side, high voltage side, 500 turns, while the low voltage side, 100 turns. And given that low voltage side is loading side, there the current is 12 amperes. Now, with understanding of the problems here, A, find out the transformer ratio. 2, the load component of primary current. First, I would like to repeat that the transformation ratio is defined as the primary turn numbers over the secondary turn numbers. So for step-down transformers, the transformation ratio is always larger than 1. So we're looking at the solution. A, as a step-down transformer, the high voltage side is the primary side and low voltage side is the secondary. These are the points. And the transformer ratio is defined as primary turn numbers over secondary turn numbers, which is 500 turns over 100 turns is 5. Remember, this is the definition of the transformation ratio. Do not confuse, Then, for ideal transformer, the high of voltage, the small of currents, because the powers is the same. So as a result, now the primary currents is the secondary currents over the transformation ratio. The loading currents is 12 amperes and secondary side. As a result, the loading current and the primary side is 2.4 amperes. So by these problems, questions, examples, hope you can fully understanding the definitions of the transformer ratio. 2, the relationship between the primary and the secondary currents. Okay, so example 2. Calculate transformer ratio of the transformer in exercise 1. Example 1. Okay, when used as a step-up transformer. Okay, so we write down the solution here. Just want telling you the concepts clearly. So as a step-down transformer, the low voltage side is primary side, and the high voltage side is the secondary side, because it is a step up, as step-down transformer. Okay. There is a wording typo. Okay, so as a step-up transformer, as a step-up transformer, so low voltage side is the primary side, and high voltage side is secondary side. The transformer ratio, of course, will be the primary turn numbers over the secondary turn numbers. Primary now is 100 turns. Secondary now is 500 turns, which is 0.2. So this telling you for step-up transformer, the transformation ratio is less than 1. So look that for the same transformer, when it is used as a step-down transformer, when it is used as step-up transformer, because the usage is different, their transformer ratio is different. Do not confuse it. The same transformer, because every year we do have students, maybe they do not skip from the lectures or tutorials, they're just looking at loads, but do not pay attention to, they think this is a simple, problems, there are simple questions. They didn't pay attention to the details of it. So they're picking confusions of it. So later on when you answer, engineering, so when your boss asks you to use a transformer as a step-down transformer, and you keep the transformer ratio, which is smaller than 1, that was ridiculous, right? Step-down transformation ratio will be larger than 1. Step-up transformation ratio is smaller than 1. So that the usage can correctly use the transformation ratios. The example 3, that furthermore to telling you, the turn number ratios, the voltage ratios, the current ratios between the primary and the secondary, and how to design, or to calculate in practice, the turn numbers required based on the voltage required and the current required. So which is straightforward one, but needs you have a clear concepts of the transformers. Sometimes the simplest question, but the students may be making the simplest errors, but in critical errors. Example 3, 2300 over 115 volt, 60 hertz, 4.6 kVA transformer is designed to have a induced electromotive force of 2.5 volts per turn. What does it mean? So 2300 over 115 volts. This is the transformer's primary and secondary rating voltage. Okay, that's it. High voltage side 2300 volts. Low voltage side, okay, 115 volts. Okay, the rating values and full load, okay, input output voltage. Working at 60 Hertz, so all the transformers be designed, working, operated at 60 Hertz. The total powers, maximum continuous powers go through the transformer, be designed as 4.6 kVA. This is total power that go through the transformer. So now, we are trying to design such a transformer so that the voltage induced across each turn no more than 2.5 volts. Well, this is a typical concept, because that in practice we have to limit the voltage induced by each turn in the transformer, so that the transformer itself, the readings, do not be overloaded, because the readings, of course, has their capabilities, to withstand the voltage. If the voltage too high per turns, that their wires may be melting down or break down or damaged or derated. So anyway, so we, for the quality issues, for long life cycles, that we have to limit the per turns voltage induced by given materials. So here telling you that, so to design a transformer so that the per turns induced voltage be 2.5 volts. Now, the A estimate the number of high side turns, number NH. The number of low side turns, here we're using the symbol N low, NL represented. And you see rated current of a high voltage side, rated power current of the low voltage side, step by step. And E, transformation ratio we used as a step up transformer, A, and transformation ratio we used as a step down transformers. The symbol we used A. Because here we already defined the symbols, so in the solutions we just directly use the symbols to represent the parameter. However, when you try to answer some questions without definitions of the symbols, you direct using the symbols. It's a not good way. Here I would like to write down that to use a symbol to present a parameter in solving problem, you have to define or declare the symbol here to use a symbols to present a parameter in solving problem, you have to define or declare so the symbol first. because in the final examination, I thought, okay, many right students are too lazy to define or declare the symbols. They directly write down the symbols, just simply say, oh, the I equal to V equal to, but no one knows what does it mean. Because even the I, the persons know that it is represent current, but which current? What currents? Okay, so current, right? We have 1,000 types of currents. Okay, so even for the voltage, we have different types of voltage. Which components voltage? Okay, which parts of voltage? Okay, which voltage? You have to define of it. Even it's a common symbols that we used to represent some parameters. You still need to declare what does it mean. Otherwise, okay, so okay, then some people right, who read the answers cannot understand at all what you are talking about. Okay. So anyway, so here to remind you, but in this semester, if you still without declaration, without definition of the symbols, when you solve the questions, you write down that as thing in the test or in the final examination. So we'll a reduction of mark. I will reduction mark. Do not say that I didn't declare that. And this moment, remind you that. Okay, so go ahead here. So since in this problems I already declared that the symbols here. So here we just use the symbols to simplify the answers. So A, that the turn numbers required for high voltage side is the high side voltage required over the design induced voltage per turn. So we can find out the turn numbers required. And similarly, that we can find out the turn numbers required for lower side, which is the voltage required for the lower side over the design per turn voltage. So which defined here is 46. And similarly, that for the transformer, the total rating powers is 4.6 kilowatt. kVA. So this total power over the high voltage side voltage, rating voltage, is the high voltage side rating current. So high voltage side rating current or design current, that is 2 amperes. This 2 amperes go through in series the coils. So with this one, the voltage cross per turn and current go through the turn. You can find out the powers per turn. The design powers per turn. So you can say for transformers also we have sometimes we have to define the design power per turn. So for this transformer, so the design power per turn is 2.5 volts per turn times 2 amperes per turn when you're looking at the high voltage side. Now we're looking at lower side, that similarly that from lower side, because the power is the same as high voltage side, and the voltage which is lower, and the current which is 40 amperes. So now Look at here, interesting is that, so this is different, right? Although the question does not talk about that here, so by this chance, we looked at for the high voltage side, although we have the same, right, design voltage per turn, but because the primary and secondary rating current is different, so the design power per turn and high voltage side is smaller, which is 5 VA per turn. But and the secondary side, low voltage side, high currents. So the design power per turn is 2.5 volts per turn times 40 amperes, which up to 100 VA per turn. So here, a question raised. Primary per turn just suffer from a burden of 5 VA per turn, while on the secondary, the burden to each turn is 100 VA. So the burden and primary and secondary is different. Okay, so therefore, in practice, the wires used for the high voltage side in this case, which with many turns, okay, and the wire used the secondary side, which is less turns, usually has different cross-sectional areas. Okay, so that the primary, the high voltage side, okay, the low voltage side, the turns per turns resistance much smaller than the per turn resistance of the high voltage side. The high voltage side, the current smaller. Okay, low voltage side, the current bigger. So the heating effects is obvious. So we have to reduce the resistance per turns in the low voltage side, so that the copper losses at low voltage side is not so much bigger than that and primary side. Okay, so generally, so the secondary coil's resistance in comparison with the primary coil resistance has a ratio of A squared. So the secondary, resistance smaller than the primary resistance, by A squared, so that the primary and secondary copper losses be balanced, be similar, be similar. Okay. So in practice, as a result, thinner wire used. So as a result, in practice, as an engineer, you should know that the high voltage side, the thinner wire used, but in the low voltage side, we usually thicker, thicker wire used. So of course, so in practice, you should thinking a lot of things, right? Okay. And therefore, then we can estimate that it used as a step-up transformer. The transformation ratio should be smaller than 1, and we use it and step down transformer to transformer ratio be larger than 1. Okay, larger than 1. That's the meaning of it. Okay, so this is about example 1, 2, 3. That is just to try to explain to you more clearly the basic concepts, okay, in the ideal transformer, okay, especially that relationship between the turn number ratios, okay, for turns by voltage induced, and the high voltage side, low voltage side, okay, the relationship between the ratios. Okay, so now we go ahead to see the example 4 to look at what talking about with these examples. Now we're talking about the impedance before the primary secondary to see that how to to transfer the impedance from one side to another side. So example 1 says that the high voltage side of a step down transformer, high voltage side has 800 turns and low voltage side has 100 turns. A voltage at 240 is applied to the high voltage side, and the load impedance of 3 ohms is connected to the low voltage side. Okay, that's the questions. Now, 1, calculate the secondary voltage and currents. Okay. 2, the primary currents. 3, the primary input impedance from ratio of primary voltage and currents. And D, primary input impedance from the concept of the equivalent circuit. So this actually to showing you why in the equivalent circuit we have draw equivalent circuit referred to primary with the secondary impedance timed with the transformation ratio A squared. But here we'll show you that. Now, so this transformation ratio, which step down transformer, primary high voltage side 800 turns, secondary low voltage side 1 turns, ratio 8. Now the secondary output impedance, secondary output impedance, that's loading impedance, which given 3 ohms. Now, so the primary voltage given, that is 240 volts. So the secondary voltage for a step down transformer is down to 30 amperes. Primary over the ratio step down, 30 amperes. And the secondary currents, which is secondary output voltage over secondary output impedance, 30 volts over 3 ohms, 10 amperes. Here we step by step just doing the calculation. Now, so from the secondary, we know that the secondary impedance be 3 ohms. The secondary output currents be 10 amperes. The secondary output voltage be 30 amperes. Now, based on the transformation ratio, the primary input currents is secondary output currents over the transformation ratio, which becomes smaller. 10 amperes secondary currents over transformation ratio 8 is 1.25 amperes. Now, if we're looking at the secondary looking at the primary, so the primary loading impedance, we're looking at primary. So the primary impedance, input impedance, is the primary input voltage over the primary input currents. So which is 240 volts. This is Ohm's law. Suppose we do not know, right? This is a transformer. This is a box. That this box concept in a box, this circuit in a black box. So this box has the input voltage 240 volts, And this box has the input currents 1.25 amperes. So what is the impedance of this box? Okay, so that's the concepts. Okay, so they also has outputs. Okay. Okay, so here we using the general concepts of the input voltage, input current, input impedance, output voltage, output current, impedance. So for any 4-terminal equipment, transformer has primary 2 input terminal, secondary output terminal. So not just the transformer, but all the other instruments. But here, this is for transformer. So this is a general explanations of the so-called input and output impedance. Okay, so these concepts, understanding. Okay, so this is very important concepts. So for the transformer, so if we're looking at the primary, so the equivalent impedance is the primary input voltage over primary input currents. But here, so the primary input voltage, primary input currents, looking at here, that, so the impedance be 192 ohms. When you're looking at the secondary, that the secondary impedance, which is given to 3 ohms, that is secondary voltage, 30 amperes, 30 volts over the secondary output currents, 10 amperes, that is 3 and 3. Okay, so now what happened of it? We go ahead, right, to see that in the equivalent circuit concepts, we found that when you at the secondary side, you have impedance Z, Z2. Z2, okay, so secondary, you have the Z2, okay. So the primary impedance, when you're looking at the second primary, so the primary input impedance, equivalent impedance, is A square transformation ratio times the secondary impedance. So this is the secondary impedance referred to primary, or the equivalent impedance when looking at the primary. So which is the so A square times 3. Okay, that's it. So equivalent circuit concepts. So these points actually prove the equivalent circuit concepts, and you should understand how and why we have got that equivalent circuit. And also here, so remind you that what does it mean by the equivalent impedance issues? But okay, the equivalent impedance issues, okay, follows the Ohm's law at any point in the systems, in a systems. Okay, so later on, when you have different types of the electrical mechanical systems, when you're talking about the input or output or equivalent impedance issues using these concepts. Here, what I draw here, so no matter what connected to you, if you choose two terminals in the systems, choose two terminals, and you got the voltage between the two terminals, and you find out the current go through these two terminals. Then you can find out the equivalent impedance looking for these two terminals. That's the concept. This is a very general concept, critical to the engineer. Okay, so learning how to define the equivalent impedance issues, okay, for a big systems that includes a lot of components. Okay, so if you can make this one, okay, a good understanding, then you can deal with many okay, electric problems easily, okay, smartly, okay, wisely. I mean, okay, okay. So that means you are intelligent, right? Okay. That's example 4 that focus on the impedance issues, how to define the equivalent impedance, refer to one side, another side for transformer side. Actually, this is applicable to any kind of the equipment, any kind of the system, 2-terminal or 4-terminal systems. You have input-output impedance issues. In practice, you may sometimes use the machines to measure some things, but the machines has also your input impedance, and the other instruments has output impedance. If the output impedance of a machine is not matched with the input impedance of another instrument, there will have the reflections of the energies between the two issues. So in practice, as an electric engineer, you have to design the system be matched in terms of the input-output impedance. Okay, you have to choose in suitable cables systems so that there is no energy reflections. But this is a little bit deep, problems. Okay, so that's the ideal transformer. In practice, then because we are using the metal wires, which may be copper wires or even other conductive wires, okay, that the wires has a resistance. Okay. Secondly, if you using the readings has leakage, reactance. So the transformer readings has 1 copper resistance due to the resistance of the wire itself. 2, the leakage reactance due to the useless flux produced by the current. And furthermore, so the core materials may cause core losses. Therefore, there are so-called core loss. The core loss can be represented by a kind of the equivalent resistance. Now, looking at example 5, taking account the practical transformer with copper resistance and primary, secondary, and leakage reactance and primary and secondary. As I just mentioned that in the previous example, say that in the high voltage side we are using thinner wires that has a relatively larger resistance. While in the low voltage side we using thicker wires that has a little bit smaller resistance. But this example just show you that. Okay. Now example 5. A 2300 over 230 volts transformer, which represents transformation ratio. 500 kVA, which represents the design or rating powers. 60 Hz step down transformer, step down, high, primary, lower, secondary. Has the following values. Primary resistance. This is coil's resistance. This coil resistance, right? Do not confuse with the core. And the primary leakage reactance. So leakage reactance, this is the leakage inductance. Leakage inductance times the 60 Hz, right? So 0.3 ohms. The secondary resistance, this is core resistance. 0.001 ohms. Look at it here, which much smaller than R1. R2 much smaller than R1. And the secondary leakage resistance much smaller than the primary one. Actually, the secondary turn numbers smaller than primary turn numbers. You know the inductance proportional turn square, right? So look at it here. The transformation ratio is 10. So the secondary impedance generally smaller than the primary impedance by the turn square. Look at it here. So the transformation ratio is 10. 10 squared is 100. Now look at it here. R1, R2, the ratio is 100, right? So the secondary times 100 will be equal to R1. Very interesting. Looking at the reactance. The secondary reactance, leakage reactance, times 100 will equal to primary leakage reactance. A square, right? Ratio square. When the transformer is used as a step-down transformer and loaded and its rated capacity, calculate the secondary and primary currents, secondary and primary internal impedances, and secondary and primary internal voltage drops, and the secondary and primary induced voltage, assuming that the terminal and induced voltage are in phase. Ratio of the primary to secondary induced voltage and primary to secondary terminal voltage. So here, what does it mean? Because there are what does it mean by this one? Sorry. Sorry. So let's draw it again. So this is the primary side. The primary resistance R1. So the secondary side. The drawings is not good, but just showing you the meanings. okay, because some students in the mind has no concepts. We have the primary, okay, terminal voltage, primary terminal currents, primary resistance, primary leakage reactance, secondary leakage resistance and reactance, secondary resistance, secondary currents, terminal currents, and secondary terminal voltage. Okay. Primary internal induced voltage. Secondary internal induced voltage. Okay, look at here. That's the relationship between the primary terminal voltage, primary terminal current, primary resistance, leakage reactance, primary internal induced voltage, and secondary internal induced voltage, secondary coil's resistance, secondary leakage reactance, and secondary terminal voltage. And looking at the solution here, that's one by one showing you the relationship between them. So remember these drawings, okay, in your notes, okay, or your mind, okay. First, so the design powers 500 kVA. The secondary V2, which is the secondary terminal voltage, secondary terminal and full load voltage. Okay, so the rating unit is assuming the machine is full loaded, the input voltage and output voltage. That's the meaning of it. Okay, so here, so the secondary, the powers 500 kVA, the terminal full load voltage 203. So the secondary current can be estimated and full load, okay, 2,175 amperes. Look, very big. And the transformer ratio here, okay, can be estimated based on the primary and secondary currents. The secondary currents can be estimated based on the primary and secondary transformation ratios. So the ratio here is 10. The ratio here is 10. Okay, so the secondary currents over the transformation ratio is the primary currents. So the primary currents, primary voltage, secondary currents. Now, the impedance, the secondary side impedance, including the resistance and the reactance, okay, which can be estimated, okay, written in complex number forms with the resistance and the reactance. Now, the primary side, this is the primary side, okay, impedance only, okay, which is the R1 plus X1 complex number forms. Okay, their difference, you look at here, so 100 times 10 squared times difference. Now, so the voltage drop, okay, secondary primary internal impedance, secondary primary internal voltage drops. So secondary voltage drops here, secondary currents times secondary side internal impedance, which is about 6.8 volts. The primary side currents time primary side, okay, voltage. That voltage drops look larger than the secondary one, okay, by 10 times. Interesting, right? 10 times. Because the currents, right, smaller than 10 times, but impedance larger, than 100 times. Okay, impedance smaller than 100 times, current larger, smaller than 10. Okay, so we can voltage drops and second. Now, assuming that the terminal and the induced voltage are in phase, that means there is no phase difference between the input and internal induced voltage. Okay. So that voltage here and voltage here are in phase, no phase difference. Okay, that means, okay. So then we can simply, right, estimation. Exactly, we should use the constant number form to calculation. But here we're just showing you the difference. Then the internal induced voltage and the primary side is the internal, the secondary internal induced voltage. Secondary internal induced voltage is the secondary output voltage plus the secondary internal voltage drops. So that's the concept. Okay. So the E2, that is the V2 plus the voltage drops, which is larger than 330 volts. And the primary internal induced voltage is the primary input voltage minus the primary internal voltage drops. Okay. So that is, right, smaller than E1, smaller than V1. And also, if we looking at the transformer ratio, we can use in the internal induced voltage E1 over E2, which we can estimate. Okay, so which is, for this case, taking account the internal voltage drops. So the actual ratios between E1 and E2 be 9.43. But if we use in the terminal voltage to the ratios, the ratio will be 10. So look at here, there are slight difference. That's because the internal leakage resistance, reactance, and internal resistance. So practice transformer is different from ideal transformer because the internal impedance. How different they are? The difference is not so big, but when we do the calculation, we use the transformation ratio as a constant. Okay. So in practice, although that for practical transformer, so although the transformation ratios when you measure using the internal induced voltage or measured with the terminal output input voltage, they are slightly different. But in practice, we generally use it as a constant to discuss about their internal voltage drops, energy losses, and so on. Okay, so if you stick to the difference between the induced voltage and in terminal voltage in terms of the transformer ratio, then the problem becomes more complicated. Okay, because this difference has a little influence on the evaluations of the performance of the transformer. Okay, but they are different. They are different. Okay, so because as an engineer, right? So we sometimes cannot, right? Not using the exact theoretic concepts to handle some problems. We're just using equivalent concept to handle some practical problems. Okay, so that the problems be solved, but efficiently. Okay, so this example 5. Okay, hope you can understanding some problems. Okay, with this example 5, in terms of difference between the practical transformer and ideal transformers. Okay, so that's the end of today's tutorial session. So we are focused on the basic concepts of the ideal and practical transformers, okay, single-phase transformers. Okay, next week we will study about the three-phase transformer in details, and also we will do the exercise on practical transformers, taking account the equivalent circuit and testing results of the transformers. Okay, see you next time. Of course, we still have several minutes. If you still have questions or problems, would like to ask me, you can write down in the chat box or by emails to me after the lectures. Goodbye.